We've been talking a lot about rocks. Now let's talk about minerals. Why? What's the difference? All rocks are made of one or more minerals. Essentially, minerals are the ingredients of rock. Minerals are defined as a solid crystalline structure that is generally inorganic and has specific chemical compositions. Here's a quartz crystal. Let's walk through that definition with a couple of examples. Quartz is a great example of solid crystalline structure. This means that atoms occur in an orderly three-dimensional array. So glass is not a mineral. There's no crystalline structure. Here's some glass. Water is not a mineral. It's not a solid. But ice is. So is this quartz crystal. Second, a mineral is generally inorganic. In all but a few cases, minerals are not made by an organic process. But this part of the definition always causes discussions. For example, there are solids secreted by animals. Aragonite limestone, for example, is generated by mollusks. Opal phytoliths are produced by plants. But the structure is considered non-crystalline. There's also a group of minerals called organic minerals. These are organic compounds containing carbon that are found in crystalline form. Examples are hydrocarbons and salts of organic acids. Organic minerals include things like amber, a fossilized organic compound, wine diamonds. These are crystals of tartaric acid. An acid that contains carbon comes close, but those are considered mineraloids. And the last component of the definition of mineral? Minerals have a specific chemical composition. It is the combination of chemistry and atomic arrangement that determines the physical properties of a mineral. So there are the three important things I want you to know. One, every mineral has its own set of physical and chemical properties which distinguish one mineral from the other. There are over 4,000 different minerals. But, and this is important, there are only a few common ones. So learning minerals isn't all that hard. This is especially true when learning the minerals that you use to identify rocks. There are around 20 common minerals that are called the rock-forming minerals. And I'll show you those in this lecture. In fact, let's look at a few of those now. Here are the light-colored rock-forming minerals. Quartz, plagioclase, here it's a blue feldspar, orthoclase, potassium feldspar, often pink, and muscovite. Quartz is a silica mineral that people recognize readily because of its relative resistance to wear. It makes up most of common beach sands. This particular crystal form is relatively common and frequently is used in displays. But quartz can occur in many colors and a wide variety of forms. It is used for many different things, from electronics to glass to sandpaper to gemstones. The gemstone amethyst is a good example. And citrine is another one, also quartz. These light-colored minerals make up what are called felsic rocks, meaning they're rich in feldspar and silica-forming minerals. At one time, quartz was used for lenses and watches, but during World War II, there were shortages of high-quality quartz crystals, so they were replaced by synthetics. Likewise, quartz is not used in computer chips. That's pure silica or a silica gel. That's a polymer of silica and oxygen. Muscovite is a mica that is usually light-colored. It has this great cleavage plane that allows you to peel off layers. There's a tendency for a mineral to break along a plane due to weak bonds. Muscovite has a cleavage in one direction, so layers of the mineral tend to just peel off. Occasionally, large crystals are referred to as books, implying that you can peel off the pages, sometimes in layers so thin they can almost be transparent. In traditional Russia, where the mineral gets its name, muscovite, it was used to make windows. Muscovite is used in electrical insulation and computer chip substrates. It also is used in facial makeup, the shiny cleavage surface, and as artificial snow for Christmas trees. Feldspars are the most common mineral group, and the name feldspar comes from the German words for field and flake, Feldspat. The name refers to both the mineral's common occurrences and the cleavage planes that have luster to them. Feldspars are divided into two groups, plagioclase and orthoclase, depending on the chemistry. If it has sodium and calcium, it is known as plagioclase. If it has potassium, it is known as either orthoclase or K-spar. Both these feldspar minerals are used in ceramics and glass, soap and scouring powders, and even making dentures. Outside of the definition I just told you, the term mineral gets tossed about on a regular basis. So in geology class, I get asked frequently, is mineral water made from minerals? Are minerals that are in vitamins and food these types of minerals? How about the mineral taste or minerality that wine tasters describe? This question actually doesn't get asked much in class. These terms refer more to elements than minerals. Mineral water is, in theory, obtained and bottled directly from a spring. Thus, it contains things like calcium, magnesium, sodium, and bicarbonate that have come from the surrounding rock. In vitamins, the term minerals refers to the components of the supplement that are inorganic. There again, the reference is more to elements than minerals, although the elements are frequently made into compounds to make them more useful to the body. Minerality in wine tasting is a tough term to pin down. Although it is a complementary term for the wine being tasted, I have heard it described as licking wet rocks. I've seen definitions that describe minerality as referring to the flavors that are not organic, that is, non-fruit, non-spice, non-herb. So that essentially brings us back to a definition that's similar to the minerals in nutritional supplements. And I think I'm good with that. So, if in a geologic sense you're not going to be consuming minerals in your water or vitamins or wine, why are minerals important? It turns out for practical geology, minerals are very important. Minerals are used to understand the formation of rocks. This is because minerals form in a wide range of conditions and environments and can record pressures and temperatures at the time of their formation. Minerals have economic value. Minerals include precious metals and have uses in manufacturing, powders, water filters, and building supplies. You can also collect minerals. Minerals in crystal form are also remarkable in their appearance and occurrence. They are relatively rare. Mineral collecting is a hobby that you can learn from and marvel over. When geologists are talking about types of minerals, they are grouping minerals into like chemistry. For example, silicates are minerals that have both silica and oxygen in the chemical formula. The SiO4 anion occurs as a tetrahedron or a pyramid shape. Silicates are the most common rock-forming minerals, and almost all rocks have one or more of the silicate minerals in them. 4 common rock-forming minerals that we talked about, quartz, muscovite, plagioclase, and orthoclase, are light-colored silicates. Now let me show you 4 common rock-forming minerals that are dark-colored silicates. These are referred to as mafic minerals because of the magnesium and ferrum, or iron content. Olivine is green or black and usually occurs as small, rounded crystals. Olivine forms at high temperatures and makes up almost half of the minerals in the upper mantle. It's one of those minerals that is an indicator of the geologic origin of the rocks it is found in. Pyroxenes are a group of minerals, the most common of which is augite. Augite is a dark-colored mineral in igneous rocks and is common in basalt. Some pyroxenes have been mined for lithium, a very precious metal. Amphibole is again a mineral group, and hornblende is the most common type. Hornblende is dark colored and looks like augite, but frequently hornblende occurs in elongate crystals, and augite crystals is found frequently in blocky form. Because it forms at high magma temperatures, fibrous varieties of hornblende are used in brake linings and fire-resistant clothing. Biotite is a dark, iron-rich mica, but it is similar to muscovite. It's really just a difference in color. Biotite mica is used in fire-resistant tiles. What other types of minerals are there besides silicates? Non-silicates make up only 8% of the Earth's crust. However, some non-silicate minerals are economically important and others occur in important environments. For example, carbonates with a carbonate ion, CO4. We've seen calcite and dolomite. They're the primary constituents of sedimentary rocks, as we've already learned, from limestone and chalk to tufa and travertine. Calcite is used in the manufacture of cement, in antacid tablets, and as an ore for calcium. Dolomite closely resembles calcite, but it doesn't fizz in an acid test. Here's dilute hydrochloric acid. The calcite effervesces vigorously. The dolomite doesn't. This is because dolomite has more magnesium than calcite and about half the calcium. Other important groups of non-silicate minerals are sulfates and halides. A common example of a sulfate mineral is gypsum, which is a calcium sulfate. Gypsum is used in plaster of Paris wallboard, and for sculpture, alabaster is a white form of gypsum. Halides are salt minerals and include halite and sylvite. Halite, sodium chloride or rock salt, is used for table salt. Sylvite, potassium chloride, is the main source of potash, which is used in fertilizers. The last two non-silicate mineral groups are oxides and sulfides. Most economically valuable minerals are processed from oxides, sulfides, and other non-silicate minerals. Examples of oxides are hematite and magnetite, which are both iron oxides and ore minerals. Sulfide minerals include galena, a lead sulfide, and pyrite, an iron sulfide, sometimes called fool's gold. The association of sulfides and economic ores has long been known, and prospectors will first try to find sulfur and then focus on an ore. In some areas, they train dogs to sniff out sulfide deposits, and then humans take over from there. So how do you determine which mineral is which? It's actually pretty easy in some cases. You identify minerals by looking at the physical and chemical properties. All it takes is getting familiar with a couple mineral properties and having a good sample to work with. It's best to begin with a clean, broken sample, unless, of course, you're dealing with a crystal you don't want to break. It turns out that broken surfaces tell you a lot about the internal makeup of the mineral. Let's start with physical properties of minerals and do chemical properties later. Mineral color is a good place to start. Think in terms of very common colors. Is it gold color or gray? Or perhaps blues or pinks? But it's important to remember that there are a lot of minerals that come in lots of different colors. Quartz is a good example. Quartz, rose quartz, and amethyst. All different colors, all quartz. Why do minerals come in so many colors? Elements, even in low abundance, can influence mineral color. For example, quartz, when it's clear, is 99.998% SiO2, silica. Rose quartz has 0.003% titanium, which gives it the red color. Amethyst has 0.02% iron, giving it the purple color. Still, as long as you proceed with caution, mineral color can give you a good hint as to what an unknown mineral might be. Looking at color also is a good way of getting your eye on the mineral. Sometimes we look at things but don't always observe. Taking notes about a sample or drawing it can help focus your eyes and your mind. You look and think at the same time. Also look at mineral clarity. For example, halite and calcite. Or is it translucent or kind of foggy looking? That might be gypsum. If it's neither of those, let's call it opaque. Another thing to look for is to see if the mineral reflects light. This is called luster. Most minerals can be divided into metallic luster or a non-metallic luster. A metallic luster looks gold or silvery or brassy, like galena or maybe like pyrite. If a metallic luster is weathered or becomes tarnished, then you describe it as submetallic luster, like graphite. There are other luster-related terms as well. When a mineral that is non-metallic reflects light, like broken glass, is called vitreous. This is a very common feature, and an example is quartz. Waxy luster looks like a candle would reflect light, like jade. Pearly luster is like a pearl. Greasy luster is like grease in rocks such as serpentine. It's really very descriptive. And if the mineral has no luster at all, then it's like kaolinite. And you might say it's earthy. I'm sure as you looked at these examples, you're thinking that different people are going to call minerals different colors and different lusters. For beginning students, that can be really frustrating, but it's okay. Most diagnostic mineral properties will depend on something that's a little less subjective than color and luster. For example, crystal form is one of those less subjective techniques of identifying a mineral. Early on, scientists like Nicholas Steno observed the consistency of crystal angle. Steno used that consistency to classify different minerals. Quartz, for example, has a very recognizable crystal form. Other examples of diagnostic crystal form include the cubic salt crystals of halite and amphiboles, needle-like structures. There are other properties that require a more physical approach to the identification process. Cleavage or fracture is how a mineral breaks. If a mineral breaks in a planar manner, it has cleavage. If the break is curved, it is called a fracture. As I mentioned, the tendency for a mineral to break along a cleavage plane is due to weak bonds. Because the mineral structure is defined by bonding, cleavage tends to be parallel. The micas we saw are a great example. We've talked about how to use a rock hammer when breaking rocks, but minerals are a bit more subtle. You can very quickly turn a mineral into a powder. But this is great. You get to break something to figure out what it is. So I'll break a couple of hand samples to show cleavage and conchoidal fracture. Biotite has a single cleavage plane. See how easily it breaks apart? Let's break some calcite. Can you see the parallel planes and angles? Count the number of cleavage planes and the angle that they form. 1, 2, 3. And they are 3 cleavage planes that are not at 90-degree angles. Now let's see fracture when I break quartz. See the conchoidal fracture? That is very typical of quartz. Mineral hardness is a relative scale of minerals' resistance to scratching. There is a quantitative scale called Mohs hardness scale. It's made up of both common objects, a pocket knife or a nail, small piece of copper pipe, glass, and your fingernail, and some common minerals. If a mineral that you have scratches glass, it's harder than 5.5. If it doesn't scratch glass, it is softer than 5.5. Quartz will scratch glass. while calcite will not. Gypsum will not even scratch your fingernail. But calcite will. The hardness scale is more or less uniformly graduated until you get to corundum and diamonds. Corundum, a hardness of 9, is twice as hard as garnet, a hardness of 8. Diamonds, a hardness of 10, is 4 times the hardness of corundum. So never carry diamond in the same container as other minerals. The other minerals will be destroyed. In addition to aiding in the identification of minerals, hardness has a practical application. For example, garnet and corundum are good abrasives. You find those minerals in sandpaper, grinding wheels, and in polishing materials. Of course, diamond is used for cutting, but diamonds used for this purpose are synthetic diamonds. Graphite is a very soft mineral and is used in industrial and household lubricants. One last common test is to look at the mineral in powdered form. In powder, a mineral may appear in a different color than a fresh surface. A simple way of testing this is with a streak plate. A streak plate is an unfinished porcelain plate. You drag a clean, unweathered surface of a mineral across the plate, and if the mineral is softer than 6.5 on the hardness scale, it will leave behind a powder. The color of the streak may help you identify the mineral. For example, pyrite. You get a black streak. With hematite, you get a red streak. Sphalerite produces a streak that smells of sulfur. Streak plates are available commercially. The point of the hardness kit is to use stuff that might be lying around the house. So don't spend a lot of money on a piece of glass and a couple of minerals. There are, of course, other tests to help you identify specific minerals. Magnetism helps identify magnetite. Smell. Sulfur minerals smell like sulfur. And taste. Yes, geologists taste rocks. Will help you identify halite. It's a salty taste. The key to knowing where to look for minerals is understanding how they form. Because minerals form in certain ways, you can expect certain minerals to be associated with certain rock types. Minerals form through the process of crystallization. During crystallization, the mineral's constituent atoms come from a source, solid or liquid, in proper chemical proportions and crystalline arrangement. A good example is diamond. Diamond is formed from covalent carbon bonds in the form of a tetrahedron, with the crystal growth through the attachment of additional tetrahedra in all single directions. You probably know that diamond has a polymorph, graphite. Both the diamond and graphite are made solely of carbon, but diamond forms at high pressures and temperatures with closely packed atoms. Diamond has a density of 3.5 grams per centimeter cubed. Graphite forms at relatively low pressures. It has a density of 2.1 grams per centimeter cubed. Crystallization starts with nucleation and the formation of microscopic crystals. Crystals are defined as a body with a natural flat surface or surfaces called crystal faces. Crystal faces of minerals are expressions of internal atomic structure of that mineral. The continued growth of the mineral results in larger crystal faces. As you can imagine, crystal growth requires both space for the crystal to grow and time. So most large minerals form in open spaces like fractures or vugs. What causes crystal growth? Lower temperatures, for example, a magma cooling below 1,000 degrees Celsius, or ice forming in water cooling below 0 degrees Celsius. Another way is evaporation of a solution. For example, salt crystallizing in an ocean. Water is removed through evaporation. The concentration of sodium chloride reaches saturation, and finally, crystals are precipitated. A similar process happens in geodes. Amethyst crystals grow as ambient conditions in a VUG change. Last is the rearrangement of atoms and ions at high temperatures. Above 250 degrees Celsius, atoms and ions in solids become more mobile, resulting in the rearrangement of these mobile atoms and ions crystallizing into a new mineral with different crystal structures. So when you are trying to find minerals, remember the mineral type and form are determined by the conditions of crystallization, that is, heat, pressure, and chemical composition. So if certain minerals crystallize from a liquid, you would search for those minerals in igneous terrains, maybe in the volcanics of the West. Minerals that form through the rearrangement of atoms would most likely be encountered in metamorphic terrains, maybe in high-pressure rocks in the Adirondacks of New York. For minerals that precipitate, you might look in rock fractures, say cracks and solution openings in limestones in the Midwest. Remember, make sure you have permission to collect and never explore in someone else's claim. So, a mineral's physical properties correspond to composition and structure. Mineral hardness and cleavage are determined by the types of bonds and distance between the bonds. Mineral type reflects the geologic environment it formed in. And minerals are a great thing to collect. Not only can you find specimens of unique beauty, if left exposed on the Earth's surface, minerals would be destroyed by weathering and erosion. So by collecting them, you are preserving them.